So hello everyone, welcome to the third lecture of the course on cyber-physical fundamentals. I'm going to continue to try to make you aware of some of the embedded systems foundations of cyber-physical systems. Today we are going to talk about models of computation. We started the discussion of models of computation during the last lecture, and today I would like to start by reminding you about what we are talking about. So I said during the last lecture that for a model of computation we distinguish between two different things. We distinguish between the components and the execution model for the components and the communication model. That means we have to describe how we would like to describe the communication between these components. Also during the last lecture I came up with this table which classifies the different models that we're going to discuss in this second chapter of the course. And I think you may be remembering that there are two dimensions in this table. In one dimension we have the communication method that we're using, and in the other dimension we have the method that we are using for describing the computation in these different components. Now this looks a little general, and you might ask, well, why don't we just use programming techniques that we are familiar with? We learned some programming, let's say in C, C++, or Java. Why don't we just describe systems in that way? We would call this thread-based computing or von Neumann-based computing. Well, we have already seen problems that arise from this approach. We know that there are potential race conditions if we access global resources. So for example, if we have some global memory, we might have problems with these race conditions. Due to the possible race conditions, we are defining so-called critical sections. These are sections of the code where we require exclusive access to that shared resource. And you may remember the fact that I introduced these P of S and V of S operations that denote the start of some critical section and the end of some critical section. In that way, we might make sure that we have some guaranteed mutually exclusive access to such a shared resource. So if we do use thread-based computing, we might need mutual exclusion to avoid some inconsistent results. And as we will see later on, we might also need some special memory properties in order to achieve some meaningful cooperation between threads in such a model. So the argument in favor of looking for other ways of describing computations are based on problems that we see for von Neumann-based computing. If in this thread-based computing we are using multi-threading or multi-processing, where we're using global variables, there we know that due to the access to global variables, we might get into these race conditions, and to avoid these we need mutual exclusion. And mutual exclusion in turn might lead to deadlocks, and we know from the theory of operating systems that avoiding deadlocks is only possible if we accept very serious performance penalties, which usually we're not willing to accept. And also, and this is not really in detail on this slide, there may be other problems resulting from the use of von Neumann computing. So for example, we know that in von Neumann computing we are specifying a total order among all the instructions, among all the statements that we have there, whereas for many applications partial orders would be sufficient, and partial orders would allow more freedom during the design of such systems. In order to demonstrate the type of problems that we might run into, I'm considering a simple example. This example is actually taken from a presentation by Edward Lee of UC Berkeley. Edward Lee made that presentation about 5 years ago at an Artemis conference at Graz. And his presentation, in turn, is using so-called design patterns that are described in a book on design patterns. In that particular case, the presentation uses as an example this so-called observer pattern, where the observer pattern is defined as a one-to-many dependency between a so-called subject object and any number of observer objects, so that when the subject object changes state, all its observer objects are notified and updated automatically. So that's a situation that we need very frequently in a cyber-physical or embedded system. So we might think of the subject object being some kind of sensor or some processor that is providing somehow processed values from a sensor. And these values might then need to be propagated to some observers. We have this very frequently in a car, in a plane, where we have a sensor, and the values from these sensors need to be propagated to many observers. So that's something that should be feasible to implement very conveniently and without requiring too deep knowledge. But we will see that in von Neumann computing, this has its problems. In order to demonstrate these problems, we are starting with a formulation of the observer pattern in Java. In Java, we can think of having a class where in this class we have certain methods, and these methods are supposed to handle this observer pattern. In order to implement this, we have a method called addListener. That's a method that allows us to add additional listeners. So these are objects that are supposed to receive notifications about changes. And also we have another method which is called setValue, which is supposed to be a method which is propagating these new values to these observers. So these methods, they work as follows. In particular, the second one, they work as follows. First of all, for convenience, we do a local copying of the new value that we would like to propagate. And then we have a for loop there where we are referring to some data structure where we have stored the current set of listeners. And then we are iterating through that data structure, and during our iterations, we are then having a call to a method called value change, which is supposed to communicate these new values to these listeners. Now the question which is raised is, would this work in a multi-threaded context where in several threads we could have calls to these methods? Well, in a multi-threaded context, we have to take into account that for a class we have kind of global data structures like the set of listeners, and we have to make sure that we don't get inconsistent results through some unsynchronized accesses to these kind of global data structures for this class. So in order to avoid this unlimited interleaving between accesses to these global data structures, we will make these methods synchronized. Synchronized means that we are introducing what some people know as so-called monitors. That means that we have a kind of implicit semaphore which makes sure that only one of these methods in this class can be active. So in this way, we are avoiding these unsynchronized accesses to the class global data structures. So in this case, we made these two methods synchronized, and now we could assume that somehow this could work. However, if we look a little more closely, we will find a remark by Javasoft. According to Javasoft, this is not really recommended code, and we might argue, well, what's wrong with it? Well, I'm going to demonstrate that there is something very seriously wrong with this. Because what could happen is the following. Value changed could call some other methods, and these other methods might attempt to acquire a certain lock on some other object. So there may be some other lock, some other monitor and value change could try to lock that monitor. However, that other object might already be held by some other method, let's say X, and X could be a method which already called at listener. And this means that this other method called X already holds the lock, and now this value change is attempting to acquire the lock, but it cannot proceed because that lock is already held and X cannot release the lock. So as a result, we have this cyclic dependency where every method is waiting for some other method to release locks, and there will be no progress in any way, so we have a real deadlock there. Now, what can we do about it? Well, we can try to avoid the situation where we are holding a lock while we are calling this method value changed. One way would be to have only the copying of the listeners being synchronized, because that's the global operation for the data structure. So we could synchronize the copying of that set of listeners, and in that way we would then have a local copy, and then while we are propagating the new values to all the listeners, we would then have released that global lock. So in that way, we could try to avoid this problem of a deadlock. But as Edward Lee pointed out, there is still a problem with that code as well. What's the problem with that code? Well, the problem with that code is that in a multi-threaded context, we might have several calls to the methods provided by our class, and this could mean that we could have several calls to this method called setValue. And we don't really know at what time we are going to have context switches between the execution of the different threads. What could happen is the following. Let's suppose we have two calls. The first call of setValue creates a local copy, then enters its loop, and maybe it has proceeded just until half of the loop until a context switch happens. And then a context switch could happen. Only half of the listeners have received the new values. And then we execute some other thread. That other thread might also call this procedure setValue with another new second value. And we don't really know in which sequence the different instances of this method setValue would be executed. It could happen that the second instance gets executed first. And that means that the second new value would get propagated to all the listeners. And only after that we might have a context switch back to the first instance of setValue. And that means that the second half of that list would get the first new value after the second new value, which means that half of the listeners would get the new values in one order and the other half would get the new values in the other order. Now let's suppose this is the position of some mouse which I'm trying to control my laptop. That means one half of the listeners is getting mouse positions in one order and the other half is getting the mouse positions in the other order. And the two listeners might get a different impression on the direction of the movement of the mouse. Yeah, so that's obviously not a very good approach. So we might try to find other solutions there. So obviously it's not that easy to actually make that code correct. Now, if we look beyond that particular example, how can it happen that we have these deadlocks? Well, actually it should not be a surprise if we have attended a course on operating systems. Because in a course on operating systems, we usually get to know that deadlocks are possible if a total of 4 conditions are met. And these 4 conditions are the following. First of all, we need mutual exclusion. And obviously, for access to global resources, we need mutual exclusion. Second condition is that it must be possible that we are already holding resources while we are waiting for more. Third condition is that no preemption is allowed, and fourth condition is that circular await exists. Now actually all these 4 conditions are met for our example, so therefore it shouldn't really be a surprise that this situation can happen. It's a result of the consequence that a concept which initially existed only for operating systems, that means the concept of processes, is now available in processing languages. So in Java you can have multi-threaded programs, and therefore you also have inherited the problems that exist for operating systems. So what can we do about it? Edward Lee came to the following conclusion. Non-trivial software written with threads, semaphores, and mutexes is incomprehensible to humans. Because you can see that there are many hidden problems that initially you did not expect. And I think it can very easily happen that you write such code and that in this code you are having serious problems. Edward mentioned that they had used this code for years, and then they had a demo at one conference, and then in the demo they had a deadlock, even though they had tried to very carefully analyze the code. So Edward also wrote the following. According to Edward Lee, threads as a concurrency model are a poor match for embedded systems. They work well only where best effort scheduling policies are sufficient. So in PC-like systems where even a deadlock might not be really a serious problem, we can use threads. But for embedded systems, for cyber-physical systems that are safety critical, we cannot ignore the problems from deadlocks. So how can we try to get out of that situation? Well, we can try to look for other ways of describing our applications. We have already seen the table where I pointed to other ways of modeling our applications. And if we are using such other models, if we are using, for example, finite state machine-based specifications, we are talking about so-called model-based designs. Also, it's already obvious that no model will meet all modeling requirements. We have already seen the very long list of requirements, and we saw that the list is so long that there is no hope that any modeling technique will meet all these requirements. So we have to focus on the requirements that are important to us, and we have to be happy if our model just meets the requirements that are important to us. And in a sense, we have to live with compromises. So in one situation, we might have to live with one modeling technique, and in another situation, we might have to live with another modeling technique. So there is no golden path towards the ideal modeling technique. In one case, we have to turn to the left, and in some other case, we might have to turn to the right. So this brings us back to this table where we see the different modeling types that I already introduced a little earlier. And this means we also have to go through the entries there in this table. I'm starting to discuss the entries in the table by first referring to the first row. We look at the first row where we look at undefined components. This is what we're using if we're talking about the very early phases of specification. During the very early phases of specifications, frequently we don't like to be too precise, because then we would need to care about details about which we possibly wouldn't like to care right up at the beginning. So therefore, intentionally, we are leaving some ambiguity there during the very early phases. There, as we will see, we can use plain text, use cases, and sequence charts are also so-called message sequence charts.